Hi there. I have Bjarne Stroustrup today with me. Bjorn, thank you so much for joining me today.
Pleasure to be here.
Today, you're working as a computer science professor at Columbia University, and I was wondering if you could tell us a little bit about what your job is about and what you're doing today.
Yeah, okay. In April this year, I retired from industry, but it seems I wasn't very good at being retired. So Columbia suggested I become a full professor here instead of just a visiting professor, as I've been for many years. And my job is primarily to give lectures and to talk to students. I have a fairly light teaching load, and I don't do that much classical computer science research because I look after the C++ standardization and the development of C++. So I'm not a very typical professor. A typical professor here gives lectures every semester and supervise students and do research and write research papers. I did that for a decade down in Texas, at Texas A&M, but here I'm concentrating on teaching, and the teaching I'm doing is mostly to do with design. How do you design software? How is software designed? What are the constraints on what you can build and how you can design things? That kind of stuff, and it relates to C++.
Like people say, retirement is overrated, right?
Uh, don't retire. It's just too much work. There's so much paperwork involved, not real work.
And Bjorn, going back in history, and you're telling me offline about your school in Denmark, and I was hoping you could tell us a little bit about your school years, like before you got to university, and then if you can speak about the Aarhus University and your master's degree in mathematics and computer science.
Sure. Let's see. I was born in Aarhus. It's a town of then about a quarter of a million people. It's the second largest city in Denmark. Denmark is a very small place, almost 6 million people these days. And Aarhus is a wonderful town. It's on the sea and it's got woods and things like that. Wonderful place. I was brought up in a working class district, and all of my family were working with their hands and such. So that's my background there. And the school wasn't great. As a matter of fact, it ranked the lowest in town. But somehow I was lucky and managed to get into high school, which was my greatest break in my career. And there I sort of learned standard stuff that you do in high schools: math, physics, languages. If you are in a country with in a small language community, like hardly anybody speaks Danish, you learn more languages. So I learned English, German, and French. And then at the end of my high school years, I had to choose what to do. And my family actually was encouraging me to take a short education because it was too dangerous to go to university. What if you didn't graduate? What if you graduated and didn't get a job and such? But I decided, well, I'll go to university. And I had the grades to do so, so it wasn't that a problem. And this was Denmark, so education is free. Still is. Let's see. Then I had to decide what to study, and I was thinking about all kinds of things the way people do in high school. I was thinking about history and psychology and architecture, um, and decided I wanted to build something. Decided that history was a great hobby but a lousy career, and I thought that math, applied math in particular, was a great career and a lousy hobby. So I signed up to do mathematics with datology, which was a Danish word for computer science, and I hadn't realized it was computer science. So basically, I got into computer science by mistake. Anyway, I studied math for a while and realized, like most people, I wasn't as good as math as I thought I was. But by then, I had discovered computers, especially computer architecture and languages, and never looked back. So my degree has a lot of math in it, pure maths, statistics, probability theory, a variety of things, and then a lot of computer science, theory, languages, data structures, machine architecture. I was very interested in machine architecture at the time, and that's how I came along to this. I still go back to Aarhus whenever I can. These years, it's mostly every summer. I'll be back there this summer. It's a wonderful place. If you ever get a chance to get to Denmark, do. And if you do, see if you can visit Aarhus. It's a good place to live and it's a good place to visit.
Yeah, I was in Denmark back in 2011. Absolutely fantastic place. Had a great time over there. And Bjorn, you touched briefly on architecture. And I was wondering if you could tell us a little bit more about how important a solid understanding of a computer architecture was for your career and the development of C++.
Yes. The architecture I was mentioning was actually building buildings and engineering, building bridges, and that kind of stuff. I really like the idea of building things, and that's pretty fundamental to the way about I think about things. When I think about computing, I think about building systems mostly. My PhD had to do with how to have hardware support for high level constructs in programming languages. So, again, this idea of building something, and especially building a foundation, because the foundation is the most important thing in everything, the fundamental, architecture. And so I studied machines to write good, solid engineering oriented stuff, foundational stuff in computing. You have to know about the machine, you have to know about processors, you have to know about caches, memories, communication channels, things like that. Um, Once you get away from the hardware, you can build applications and web apps and such. That's great, and we need them, but it's not what I think most about. When I think about um, computing and computers, I tend to think about things that use computers. It can be, well, a smart watch or a car or a spaceship. I mean, I really love the idea that there's C++ programs running on Mars and the new Webb space telescope out at the L2 Lagrange point. This kind of thing inspires me and makes me excited. And the kind of stuff that runs these things at the bottom level, right at the interface between the hardware and the software, is where a lot of interesting and important work is being done.
Can you tell us a little bit about when you learned the fundamentals of object-oriented programming? I think was you did some work with Kirsten Nygaard from Norway, correct?
Yes, Christian Nygaard, who invented object oriented programming and the language Simula, this is where you got classes and class hierarchies and virtual functions, that kind of stuff you got from Christian and Ole Johan Dahl, his colleague in Norway. Anyway, he was coming down to Aarhus from Oslo about a month, once every month as a guest lecturer. And it so happened that his guest rooms were right near where my office was. I shared an office with some students. And so when he came, he He just went up to his room and stuck his head into my office and says, basically, round up the usual suspects. That is, find some students for him to talk to. And then I did that, and we went up and we sat and we chatted. And basically, talking to Christian Nygaard is a bit like drinking from a fire hose. That is, you don't get to say very much because once he gets started, he has to stop. So basically, once a month, I was sitting for a couple of hours listening to him talking about the world and programming and systems and things like that. And in the process, I learned the foundations of object oriented programming. And yeah, I of course also picked up the syntax and the language details at other places. But for him, I got the philosophy: what is it for? What does it do? Why is it the way it is? That was very inspiring.
You mentioned your PhD work at the University of Cambridge, and I was wondering if you could tell us a little bit about what the work was all about and how was your time at Cambridge.
Sure. I had a pretty good and tough time in Aarhus, doing math, doing computer science, learning the basics, not coming from a educated family. I didn't have any background in that, so I had to work my way through it. But I got more and more interested in interesting hardware, microprogrammable computers, interesting machine architectures. And so I looked at where they had interesting machines like that. And there was some in London, there was more in Cambridge. And eventually I applied to do a PhD in Cambridge after I got my master's in Aarhus. And Cambridge is another one of those magical places. Wonderful research environment, quite good social environment. The college system in Cambridge means that you're part of a relatively small group of people, 200, 600 people in your college, which is your home base. And then you have your department that, again, they were not that big, 50, 100 people. So you weren't lost in a humongous university. And so you could learn a lot from individuals. My advisor there was David Wheeler, who was seriously smart and did a lot of good work. He had a reputation for being the laziest computer scientist ever. He was willing to solve any problem, however hard, to getting out of work. He built some of the first advanced caches. He implemented the first capability based machine hardware protection for everything. And his advising style was interesting. I tended to come and see him once a week, which is not uncommon for PhD students. First of all, he told me that he wasn't going to tell me what to do. As a matter of fact, he says, "You know what the difference between a master's degree and a PhD is?" And I said, "No." He says, "If I have to tell you what to do, it's a master's." And I said, "Well, I've already got one, so we're not doing that." And so every week I come and I explain to him these great ideas I've had over the week. Young PhD students are always full of great ideas. And so I tell him that, and he says something roughly equivalent to, "Yes, yeah, yeah, yes, Bjarne, that's not a bad idea. Yes, we almost did that in the ETSAC 2, but..." Now, the ETSAC 2 was done while I was still in short trousers. So that was slightly embarrassing. And then he explained what was right about that idea, what was wrong about that idea, what they did instead, what was wrong with that, what was right with that. So basically, he talked for an hour about design issues. And so you come in feeling great and you go out feeling very small because you realize that everybody had thought about all of your good ideas long before you'd seen a computer. Some people didn't like that much. I loved it. It was great. I learned a lot. And eventually, one day, David Wheeler said, "Well, yes, that's interesting," as opposed to explaining how he had done it 20 years before, and that ended up being my PhD. And like other good departments, there was people you like to hang out with, other students, you talk to other professors. Roger Needham was one person I talked a lot to. By the way, David Wheeler was the one that formulated what was known as the first law of computer science, which is every problem in computing can be solved by another indirection, except, of course, for the problem of too many indirections. People tend to forget that caveat at the end, and so they build horribly complicated systems with too many interactions. David Wheeler was also the first person to write a program and get it to run on a modern stored program computer.
Bjorn, you mentioned before Simula, and I heard another interview where you mentioned Algol 60 as well. And I was wondering if you could speak a little bit about the influence that Simula, Algol, and some other languages may have had in the creation of C++.
Okay, yes. My first programming language was Algol 60 on on an old Danish computer called Gear. And this was one of these computers that had a desk and filled a room, and you started it with switches. But it was programmed in a high level language, Algol 60. So from there, I learned about the structure of languages, grammar, type system, and things like that. And it wasn't all that flexible, there was no I/O. When Simula came, one of the things that attracted me mostly to it was I could build my own types. In traditional programming languages, you are given a set of types like integer, floating point numbers, strings, and that's it. You live with that. In a language like Simula and later C++, of course, you can build your own types. So if there isn't a matrix, you build a matrix. If there isn't a coroutine, you build a coroutine. If there isn't say, a digit buffer for a telecommunication system, you just build one. And that was a key thing I learned there. So from Algol, I got the structure, the traditional language structure. And from Simula, I got the idea of building your own types, building basically your own little programming world that suited your application. The weakness of those languages was that they were rather expensive to run programs in, and they couldn't touch hardware. And at the time, I was very interested in hardware, interested in microprogramming, interested in operating systems and such. And those languages couldn't quite get there. There was a wonderful set of languages on a set of machines from Burroughs where there was hardware support for the high level languages so that you could do interesting things with it. But mostly you were stuck with the language you had. And that influenced me when I came to Cambridge. I tried to build some system simulations in Simula, and that was done very nicely. Good programs, fairly elegant, but they ran so slowly that I was bringing the university mainframe to its knees. And as a grad student, you only do that once, then you're kicked off and never again. So I had to look for something that could do what I wanted and fast enough and cheaply enough. And so I built in BCPL, which was a local systems programming language and actually an ancestor to C. And I got my system built, I got my data, and I got my PhD. But I was very convinced that if I ever got into building a system again, I would not do it with inferior tools. And the tools had to be something like Simula that allowed me to build my own types and have good static type checking and that kind of stuff, and something that could run fast enough and touch hardware. And if you think about it, you can see there's the origins of C++ because when I came to Bell Labs, I got exactly that kind of problem that required both high level and low level facilities.
What led you to decide that you should invent C++?
After my PhD, like many PhD students, you decide that you want to do something like what you did for your PhD, but grander and better and such. And so instead of simulating a distributed system, I thought I would want to build one. And we had Unix. This was the lab where Unix came from, and Linux is a sort of a clone of Unix. Um, and so that was an obvious thing to try and see. If you want a distributed system, let's split the Unix kernel onto several machines so that you can have cooperating um, processes running on different machines, possibly communicating with a shared memory, possibly communicating with a network. So if I had actually built that system, I would have built the first Unix cluster or something like that. But yeah, it turned out that I couldn't do it. Um, Not for the fundamental reason that I probably couldn't for any reason, but because I didn't have the right tools, and I had decided in Cambridge I would never again attack a problem with inferior tools. And so I knew I wanted something high level like Simula, and I wanted something low level, and the local low level language that could do process schedulers, memory managers, network interfaces, and such was C. Um, Dennis Ritchie was just down the corridor from me, so was Brian Kernighan. Really great people, very smart, very nice people. And so I decided I would have to somehow merge the ideas of Simula and the ideas of C into one language so that I could build my distributed system. And so first came what was called C with classes, which was exactly what it was. You take the class concept and put it into C, and that worked rather nicely. And so it turned out to be useful, not just for me, but for some of my colleagues and such. And so instead of getting my system built, my distributed system built, I became a tool builder and supported my friends and colleagues with C and with C with classes, and later it was renamed C++.
And Bjarne, do you still remember the first time that you showed C++ to some of your colleagues, and what was the reaction?
I don't remember the first time. Bell Labs was a great place, very friendly and collaboratively. So I undoubtedly talked about all kinds of things early on before there really was a language, before it all gelled together. But I do remember um, some people liking the idea of building their own types and building it so that they could afford to use them. For instance, operator overloading came in because some of my colleagues were simulating machine architectures and they needed and or and XOR as their fundamental operations. And so, if I had to have those operations, of course, I would throw in plus, and multiply, and minus also while I was at it. And also at that time realized that overloading assignment and subscript and function call were important things. But basically, it came out of the fact that people liked the language, liked the two types, but they wanted a notation that was familiar to them. There was problems. I tried some incompatibilities with C and was told that no, they couldn't do that. I shouldn't do that. I had to stay compatible, or my users couldn't actually use what I was building. I had some problems with class hierarchies and virtual functions because people says, well, if you don't know which function you're calling, you haven't done your analysis properly. And of course, with a virtual function, the point is you don't know exactly which function you're calling, but you know that you're calling one that has roughly the right semantics. And so they said, well, why don't you use function pointers? But I said, they're too disorganized. They're not part of a type system. It's too easy to make mistakes. And eventually I challenged some of them to write the classical shape example with in without inheritance. And they could all do it, but they all made two or three mistakes before they got to the correct solution. And I said, see, if you had the support, you wouldn't have made those two or three mistakes because the compiler would have made sure you got it right the first time. And so I slowly convinced people by practical demonstrations and by um, addressing specific problems they had, like for the overloading thing. And I think the breakthrough was when I found bugs in telecommunication software. Um, I mean, telecommunication software has to be very, very reliable, and by using my type system, especially constructors, destructors, I found latent bugs that they hadn't gotten right, and so that convinced people that there's actually was a value to this more uh, more architected, more deliberate designed code.
Bjorn, I was hoping you could tell us a little bit more about the work you put into C++ to make the compiler so effective in generating, at the same time, performing code, but it's also very stable, very safe. Can you tell us a little bit about that?
Yeah, I started out with uh, compatibility with C because C had decent compilers, and I decided to stay compatible with something. Otherwise, I would have to build everything up from scratch, and that takes a long time, and it's probably not very effective. The way I said it, well, you could, if I build it myself, you would get my errors. If I stay compatible with C, you'll get Dennis's errors, and he may have fewer errors than me, and apart from that, we know his errors. So stick close to C. It's culturally compatible. The only thing I couldn't handle was that C didn't have function argument checking at the time. Um, the function declarations with function arguments, the function prototypes, is actually my handiwork that found its way into C. So that was the incompatibility I put in, and I was criticized by people for at least 10 years, people who were very conventional and didn't want the type checking. Now, once you build a type, you need to be able to use it efficiently if you are going to use it for systems programming. And I was memory managers, process schedulers, device drivers, that kind of stuff. And I want to use abstraction. I wanted to use user defined types. And for that, I needed not to cross protection barriers through code. I wanted the compiler to deal with it. So the checking has to be in the compiler. And I also wanted to make sure that I could afford to call functions. So I needed to be able to do inlining of functions. And basically, the combination of static type checking of interfaces and inlining of small operations is the key to the performance. And then, of course, once you can do that, you can go in and you can do things that you can't actually do in the language with, say, embedded assembler uh, or code that takes advantage of knowledge of the hardware. That's how you get the real efficiency down at the low level. These days, you can get to FPGAs and GPUs that way. It's not something that has gone out of fashion. Basically, the fundamental ideas of high and low level code and tuning to the hardware has weathered very well over the years. There's always people that says efficiency doesn't matter, and the counter argument that I come up with that it matters somewhere. It matters down close to the hardware. It matters when you have a small computer. It matters if you have a huge server farm and you have to pay for the electricity. So performance matters, and most of it is in the infrastructure down close to the hardware, where my main interests lie.
It's fantastic. And Bjorn, C++ is used all over the world, literally, and like you mentioned earlier, it's running on devices on Mars, and it's on a space telescope and a number of other devices, right? And it has had an incredible impact in the industry and has generated jobs to thousands, if not millions, of people all over the place. And I'm just wondering if you could share a little bit some of the ideas and some of the improvements that you're thinking about bringing to C++ for the future.
Sort of the best number of current C++ programmers that I have heard is in the region of 7 million. So it's large. And yes, it's all over the world, and it's in all industries: finance, gaming, electricity, oil, science. I was very happy when I was visiting CERN to see how they were doing the physics research using it. So that's fine. But how can it be better? C++ was designed to evolve, actually designed to change. But to evolve, you have to have a stable core that doesn't change while you provide better facilities. And that was very early ideas. I was reading some old notes of mine from way back in the 80s, and those ideas I just said here was there. I was actually surprised. I thought I had thought of that a little bit later, but I hadn't. It was there from the beginning. And so there's people that says, why isn't C++ just stable and doesn't change? Well, it is stable and it changes. That's the idea. Um, Currently, we're getting C++ 20 into place. Things like concepts that makes generic programming much better typed than it used to be. Basically, as strongly typed as ordinary code with types. And we have modules coming that speeds up compilation uh, a lot, like 5, 10, 25 times faster compiles by cleaning up your code and your interfaces. And for the future, we are looking at things like static reflection, being able for programmer to write code that says the properties of that class there I'm going to use in designing a new class. So for instance, I can say I want to have a little function that writes JSON parsers for a specific set of types, thus optimizing the reading and writing of those types. That's one thing. The other thing is that we're looking at functional style pattern matching to get a more type safe and flexible way of expressing alternatives. A lot of work is going on in libraries, so we're working on a general model for concurrency to be used in libraries. Well, I probably shouldn't talk too much about future because most people are still trying to catch up with the current. And when people talk about the future, people think that they're going to get it tomorrow or they'll get exactly what's being talked about. That's not the way it is. For a large standardized language, it takes 3 or 6 years to get anything done. And the ideas, the designs mutate along the way to fit into the language, to fit more people's needs and such. So don't be too excited about the future. First, try and use the existing language better. That's where most of the benefit for most of the people are.
Going back to the past a little bit, and you mentioned the financial sector here, and I was just wondering if you could tell us a little bit about your time with Morgan Stanley and the work that you did over there.
Okay, so first I worked with Bell Labs. This was great. It's the greatest place on earth for practical research into computing of all sorts. with great colleagues and such. And after 20 some years, the economic situation in the world changed, and it was hard to maintain an organization like that. So it became less interesting and less exciting. So I decided to try and move um, to academia. Basically, my children had gone to university and was having a lot of fun. So why shouldn't I? So I went to become a professor at Texas A&M, which is a good engineering school, and I had a few good years there. But then I thought I'd done all the things that you do as a professor. I'd written applications for grants. I'd graduated PhDs and master's students. I taught undergraduates. I taught graduates. I'd written practical research papers. I'd written theoretical research papers, gone to a lot of conferences, things like that. So I've tried all the fun things. And then I felt that it was necessary for me to get back to industry to see where the real problems were. Uh, Getting back to the cold face, as I was saying. And at that time, also, I was getting grandchildren in New York City, my daughter's family. And so, when, to my surprise, I got a job offer from Morgan Stanley, I didn't, well, I did say no, but I did listen. And I didn't quite understand why I should work. I mean, you're a bank. I mean, what's there for a computer scientist? And it turned out that they had really interesting problems, mostly to deal with communication, but also some with interesting high-speed computations. So there was enough real problems for a computer scientist to work on, and they gave me a lot of freedom to work on the C++ future and such. So, and they were just 20 minutes from my grandchildren, so I moved to New York. I think there always are both professional and personal reasons for choices. And if there isn't, there should be. You have to aim for a balance. You can't just be a research machine or a development machine. You have to be a person also. And this was the case here. And so I moved to the bank and I worked there for 8, 9 years. And then I retired because now I had tried all the interesting and fun things there. And it was hard to do research with COVID raging. And so I thought I was going to retire and not work full time anymore. But well, Columbia convinced me that that would be a mistake. And so I'm now sitting here in my temporary office at Columbia talking to you and planning my lectures and all of that kind of stuff.
It's absolutely fantastic. And Bjorn, you're still, you have lots to do still, right? So, but looking back in what you have done to date and so many accomplishments in your career, is there anything special that you think you'd have done in a different way if you could?
I don't know. I think my biggest personal problem is probably that I can only do my work in or near big cities, and I actually like smaller towns and more countryside things. The decision I made to do computing also determined where I could live. And I didn't know that. I was a young lad at the time and didn't think that far. And so decisions have consequences. In terms of language design, I think I got the big things right, and all the little things I could probably, in retrospect, do better now. But you don't get a second chance, not when you have users. Once you have users, you have responsibilities, and you better live up to them. Yeah, also the other thing, my decisions to do research and do advanced work at that time meant that I couldn't live in Denmark because that wasn't done there yet. Today, I could probably do it differently, and I might very well not have moved to England and to the States. So I think in technical things, a combination of good choices and good luck, I've done reasonably well. So I'm thinking about personal things, and I haven't done badly at all. But when you ask me to do such a reflective question, I think about it.
You have done so much. You had an impact on so many different lives all over the world. Like you said, 7 million people using C++ to create products. Is there anything in particular in technology that you'd like to work with one day that you have not had a chance to work with so far?
There's so many, so picking one is just too hard. I doubt I will get to work sort of full time on a particular um, application again. I have to write my articles, I have to write my books, I have to give my lectures, I have to work on the standards committee. That's more than one person's job. And I also want to live. So I'm not going to go into product development again. Um, I talk to people a lot. Um, a friend of mine, Vincent Lestrade, is building some really interesting stuff to try and put SQL out of business by providing better semantic guarantees. That's interesting. That's not my field. That's probably why it's interesting. I've never done real data management and such. And he has. He used to run Amadeus's computing development department. Amadeus is the ones that sells you your plane tickets if you use any of the major airlines. So that's an interesting thing. And I think this answer is typical. That is, I bump into something through friends, through accidents and such, and interesting. So I get interesting and I do a little bit about it, but I don't have the ability to just say, okay, I'll do this for the next 5 years to do it right. I can at most help people and take an interest.
Like I mentioned to you earlier in our offline conversation, the programming group that we have, there's substantial amount of young adults. They are trying to figure out if technology and computer science and programming is something that they should take in their lives and maybe develop a career. And I'm just wondering, what kind of recommendations do you have for those that are just starting and in a similar way to the beginning of your career, trying to understand what's computer science and what's programming? Any specific thoughts you have for those?
Probably not very specific because you can only give specific advice if you know specifics about the background and interest and the skills of the person you give advice to. But in general, look out for something interesting. Look out for something you're good at. Usually, interest and what you are good at are related, and get as much education as you can and work hard because, well, in most fields you are actually competing with everybody on earth, and you if you don't work hard, uh, then you probably won't succeed. Also, foundational stuff is important because that's what doesn't change. If you specialized in a very particular specific thing like programming some particular kind of web app in some particular kind of tool chain, you'll find in 5 years it's not there anymore. You have to learn a new tool chain, a new set of applications, a new domain of the application. So, if you have a good foundation, you can make that shift without too much trouble. But if you've just bet your whole career on one very specific thing, the odds are that you won't be able to move. So work on the foundations, work hard on the foundations, and then look for things that you find interesting and you find that your skills match. If it's a real pain to do it all, it's probably not the right field. If you feel that you're actually having some fun, if you feel that it's not too painful to get the necessary and unpleasant things done, that's probably right. There's this saying about research, which most people don't get to, which is the simple statement about research. You mean they pay us to do this? They pay us to have this much fun? That's probably the ultimate.
It's those are great recommendations. And talking about recommendations, do you have any book or music or movies or anything in particular that you may like and you'd like to recommend to the audience?
I don't know. I listen to a lot of music, even um, when I work. Um, there's Beethoven symphonies, especially in the ninth and the sixth, are very nice. I like Greek. Um, there's so many. Um, Elgar. Um, there's lots of classical music I like, and then I like sort of the what is now old rock, Fleetwood Mac. Just thinking about what I've heard of recently, I even listened to one of the old Beatles albums lately. So yeah, rock and classical. For books, I read a lot of history, just about any history. I was just reading a book about the Spanish Civil War, for instance. Can't recommend you that one because it's in Danish, but there's undoubtedly good history books in Portuguese also. I read classical history, Roman, Greek, medieval history, also a fair bit about Asia. I must say that I don't know that much about Brazilian history or South American history. Probably more than most Americans, but still, I feel that's a bit of a weakness of mine. It's again this kind of thing. There's so much interesting stuff in history. Somebody asked, "What's the difference between fiction and history?" And the answer is fiction has to be plausible. History just is.
We have been speaking for close to 1 hour. I realize I could spend 10 years speaking with you because there's infinite number of topics that we could speak about. I'm just wondering if there's any questions that you believe I should have asked you today and I did not.
We've been all over the place. I think there's a good set of questions. I think if I have to say something towards the end, is look for a balance in your life. Work hard, but also have fun. Think of family. Think about place.
Is there anything in particular that you'd like to share in terms of contact information or anything else you'd like to mention at all?
I don't think so. If people want to find me, they can, and it's probably a good idea that they have to spend at least a couple of minutes doing so. I get far too many messages and contacts, more than I can handle.
I can imagine, and you so graciously replied to me, and it's been a great privilege speaking with you today. And thank you for taking time, and all the best to you. And I look forward to seeing whatever you come up with in the future.
Sure, and good luck with your project here. Good luck to uh, the people in your group. Bye.
Thank you.
Chegamos ao final de mais um episódio. Agradeço a todos a atenção e o nosso site é osprogramadores.com. Participem e até o próximo episódio. Um bom dia para todos.